I'll begin with a word of prayer. So, you guys can work together, that's fine. Okay? I'll begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Again, I thank you for this class, for this opportunity we just have to meet, study your creation. Just pray that you guide our steps today. Help us to glorify you in what we do, Lord. And we just, again, thank you, Lord, for your many blessings. In your name I pray, Lord Jesus. Amen. So, as you guys can see, we have a visitor today. He's, he's working on an oversized paper airplane at the moment, I would say. I don't think newspaper really works for paper airplanes, but okay. Yeah, I guess we'll see exactly. So, we're talking today about surface integrals. So, so the line integral, just to recap, what does it do? It essentially counts how much a given vector field aligns with a given curve, right? If the vector field in principle was, of constant magnitude and it was perfectly parallel to the curve in question, then the line integral would just be the magnitude of the vector times the length of the curve. Whoa. Nice.
You succeeded.
You gotta get down from the chair to try that out. I mean,
I'll make another one.
yeah. Well, you can. Are you gonna make another one first? Okay. Well, great. So, like, the integral along a curve of f dot dr would just be equal to f times the length of the curve, right? In the special case that the vector field was parallel to the curve, right? So that's essentially what the line integral is calculating, the so-called circulation, how much the vector field aligns with the curve. So for the surface integral, the basic idea is that if you've got some surface, right, and you have to define a direction for it, like a normal. So if that's a surface S, and that's the normal, and if your vector field is, it's got field lines that look like this, right? If they're just going directly through and parallel to the normal, right? If you can picture that. All right, then the flux is equal to the magnitude times the area of S. All right? So that would be the simplest case, is that you had a vector field of constant magnitude and you had a flat plane. Well, you could just say the area of the plane times the magnitude of the vector field. That's what we're going to define to be flux, right? So in other words, it's a way of counting the number of field lines that go through the area, right? And of course, the first thing you could do then would be, well, really the flux, we'll use phi for flux usually. You could say F dot n hat times the area of S, right? That would be the next thing you could do to further, bring nuance to your way of calculating flux, right? Then if the vector field doesn't exactly align with the area, we can still account for the flux, right? For example, if the vector field is tangent to the surface, then we don't get any flux because none of the field lines pierce the surface, right? They just travel parallel to it. So in the case that the vector field's parallel to the surface, we get zero flux, all right? Which is kind of exactly counter to, that was for coloring. That was, well, you better color that plane. I'm starting to think this might have been a bad idea. Well, he's behind the monitor. The camera can't see him. It's funny. Oh, there he is. Yeah. All right. So we want to figure out how to calculate the flux of a vector field over a curved surface. All right. So let's talk about how to set that up. So here's maybe my surface. I usually draw it like this just for the sake of, picturing it. So it's a surface in 3 dimensions, as usual. And if we talk about a particular point, right, of course we can, let me go ahead and erase this stuff over here. So let me not take too long. At the moment, I'm just motivating the definition of the surface integral here. So let me not let this drag on too long. For the way to describe a surface, right, is we have a domain, which if we use V and U, that's my parameter space. And basically, we've got a patch, which we could either use a big X, sometimes use a big X vector for the parameterization, right? So like the parameterization, it's got what? It's got X, it's got Y, and it's got Z. It's a parameterization of the surface, right? And as we look at a particular point over here, right, like let's say U naught, V naught, that maps up to a particular point up here, right, X of U naught, V naught. And so I can look at like a little a what?
A horn.
A horn. A horn. Okay. I'll allow it. So we can look at a little, a little square here, right? Which would have, like delta U for the side and a delta V for the, delta U, delta V square, and see what that maps to. What is it going to map to? It's going to map to, up here, some sort of like little, curvy patch, right? So here's the, this is the image of, let's say, how to write that. Well, there you've got, let's see here, I'm going U naught to U naught plus delta U, Cartesian product with V naught to V naught plus delta V, okay? So it's specifically X of that. All right, so this is like, it's a curvy little, it's a little subset of our surface, right? A little kind of curvy parallelogram, okay? And so to a pretty good approximation, well actually to a very good approximation, if this is a normal surface, a letter A, it's not bad. Yeah, okay. Like the Avatar logo. Oh, I hope not. Let's see here. So, sorry. I could never get in that movie. Let's see here. So this point again, let me call this point P naught just for the sake of giving it an easier to write label. And so through P naught, there's 2 different tangents to the surface. Do you remember? We can talk about the coordinate curves, either fixing U or fixing V, right? So, and to those coordinate curves, right, like this, we have, whoa. Well, you go try it. Come on here where you can, there you go, try it out. Well, better try it again. Yeah. think you may be distracting my students, Benjamin. All right. Let's see here. So this would go in like the x hat sub. I'm fixing u, but holding. I'm fixing u, but varying v. So this would be like xv, and this guy right here would be the x u, right? So you've got the partial velocities, partial x, partial v, or partial x, partial u at that point, that give you the direction to the tangent vectors, right? So if you want to envision that, you could imagine that if you fill out, like there's like a little pretty good approximation, if I can draw it again here. So just focusing on the point of tangency, it's something like, to a pretty good approximation, you've got this like little, this little, okay, so the surface may be dropping out from under it or something, but to a pretty good approximation, this tangent plane, this little tangent plane. Did you guys ever watch the Ninja Turtles? Yes. Do you remember Shredder? It's kind of like that. Like these are like scales, if you can imagine, because there's not just one box. There's infinite, like there's a whole series of boxes here, and so you would be like sort of imagine filling this surface with scales. Let me draw it again, just to illustrate the scale idea. So something like we're approximating the surface with like little, all right. And then the question is, so that gives me a way to replace the surface with like a tiny little plane that's pretty close to the surface, approximately speaking. What's the normal to my little purple surface? So like the normal, we can get from, we've got our xv and we've got our xu, right? So without loss of generality, we can calculate the normal to that vector, normal to that surface, right? And that would give us something like this, xu cross xv, right? That defines a normal to the surface, a so-called normal vector field. So if I want to calculate the flux that goes through like just that one little curved rectangle, what would it be? And of course, I'm talking about the flux of a vector field which is given, but I have not yet pictured, right? So maybe the vector field looks like this. I don't know. It doesn't really matter what the vector field looks like exactly. It can point every different which way. The point is, if we look at it right here, right? Only the part of the vector field which is perpendicular, right, to the surface counts as giving flux, right? Or more to the point, if we go back to the thing I erased, the flux through this little one, the flux through just this little patch here, which I could call a little bit of flux, it would be, xu cross xv, right? That dot product with the force, right? My bad. I'm sorry. Benjamin, you're distracting me, dude. Well, yeah, that's the thing, is I haven't quite done it justice, right? So the length of this, all right, so how to get the point here? If these wouldn't be, I should really multiply that by what? By like delta V, and this should be multiplied by delta U in order to get the length of this and that, all right? And that's right, so then the cross product, if I look at x, v, delta V, cross product with xu, other way around, my bad. I got to do the u first, I got to do the v second, that's the rule. So if I do xu delta u cross product with xv delta v, the magnitude of that should be equal to the area of the little, well, it's not the area of the actual surface, right? That would be the area of the tangent plane approximation to the surface that corresponds to this little delta u and delta v, all right, at the point u naught. And so, whoa, yeah, okay, well, let's get it out of our system. Go ahead, fly. No? All right. So if that's the area, then the little bit of flux here would be, the magnitude of the cross product of the partial velocities times the f dot what? Oh, my bad. Son of a gun. Ay, ay, ay. So it would be x, I really should have given this thing a name like 3 minutes ago. xu cross xv. See, I keep writing xu cross xv everywhere, right? So that dotted with the force times delta u delta v, that would be the flux that goes through the approximation to the surface, right? The little tilted tangent plane thing. Does that make sense? I hope. Yeah.
Can you always assume that delta u and delta v are perpendicular?
They're not. Delta u and, well, okay, so over here, sure, because we set up our parameters to be, in the UV space where they're taken to be Cartesian coordinates, fine. But is the partial velocities perpendicular? Not generally. But we do need to assume this much. We do need to assume that the partial velocities are not collinear. See, if the partial velocities were collinear, then this wouldn't be a good parameterization. It wouldn't be what's called a regular surface. All right, so.
So how can you have the delta u and delta v as the area?
Well, delta u and delta v, those are just the displacement. I mean, that's just a little change in u and a little change in v over here. Those aren't vectors.
But that delta u delta v is the area of that specific.
Well, I mean, technically it's the area of this little square over here, I suppose. But this right here, so basically that's like the length of this and the length of that. But taking the cross product accounts for the fact that they might not be perpendicular. That breeds the angle, whatever the angle is between the two vectors, right? It takes the magnitude of the lengths of the two sides times the sine of the angle between them, which gives you the area of the parallelogram. And then what we do is we simply add the flux from each little rectangle up, and that gives us a very good approximation to the flux through the whole surface, right? So so the flux, something like, the sum over I and j of, let's see here, so we do f, we have to evaluate the f at x hat of ui vj, right? And then we take the dot product with the normal vector at x of, well, let me just say the normal vector at ui, come on, ui vj, delta u, delta v. Where here I'm partitioning the domain. I'm partitioning the domain into a collection of little boxes indexed by I and j. And then what do you do? So that's just an approximation, right? That's an approximation to the flux. And so how do we get the exact flux? We take the limit as the delta u and delta v. Why did I get you rubber bands? So you guys probably enjoy this lecture more than the ones I've actually accomplished deeper things. Like he's doing what you all want to do. But Anyway, so in the limit, as delta u delta v goes to 0, which is, of course, exactly the same limit as the I and j go to infinity both, what does this become? It becomes the integral, right? So for these reasons, we make the following definition. If S is surface parametrized by X, a mapping from D, which is a subset of R2, of course, to S itself, which is a subset of R3, and the normal vector, UV, which is by definition partial X, partial U, cross partial X, partial V, is not equal to 0 on D, then S is quote-unquote regular surface. It's a regular surface. And if F is continuous on and near S, then we define the flux of F through S by the integral over S. And this is debatable. Some people would put a double integral here. I kind of go back and forth. If you write a single integral here, I wouldn't complain, actually. You give, are you going to give tickets? Okay, he said he's going to give tickets if he saw people using phones in class. So, so what this is the double integral over the domain. We take F, we evaluate it at the parameterization. All right, we take the dot product with the normal, and then we integrate over du dv. So let's see here, some notation. So notation, the ds vector, if you just want to think of it as a mnemonic, you could think of it as, it really is partial x, partial u cross partial x, partial v times du dv. All right. But you could also write that itself as like the magnitude of partial x, partial u cross partial x, partial v, the magnitude, let's see here, times du, dv, and put it in the n hat direction.
And also no tablets.
In the what?
And also no tablets.
No, some people use tablets to write notes. That's okay. We can't stop them from doing that. For they take very neat. Oh, hey, no headbutting. This is not a problem I usually have. All right. All right. All right. I think this is your last time this semester, little man. You're being a bad example. Where'd you get that pen? I'm going to show Mom the video of that later. You're going to be in trouble. Hey, Benjamin. Can you color? Uh-oh. These things will happen. All right, so n hat. This is the danger with comedy. Sometimes you go too far. Let's see here. N hat is the normalized. So what that is it's just, you take partial x, partial u, cross partial x, partial v, and we divide by the length of the vector. All right, and so just to finish this notational, Benjamin, it's okay, buddy. You did not hurt me. Okay? All right. Here you go. Ah! So this right here, I would call ds. Go sit down. Good color. So, so ds is the infinitesimal surface area element, whereas ds vector is the infinitesimal vector surface area element. For example, if I wanted to calculate the surface area of a parametrized surface, how would I get that? By almost the same thing I've set up already here, guys. So, I mean, we might as well just define it while we're at it. The integral over the surface of like a scalar function times ds is just equal to the double integral over d of f. You just evaluate at the parameterization, and then you multiply by ds, okay? Same ds. So this is the so-called scalar, the integral with respect to surface, the scalar surface. Oh man, I forgot the name of this thing. I can tell you this, when we put f equals to 1, it gives you the surface area, all right? Another way to look at this is if you wanted to calculate the surface area, you just take the, calculate the flux of the unit normal to the surface, and that would give you the surface area. It's another way to look at this. All right, let's, yeah?
That is a vector, the whole integrand there.
This one?
Yeah, because you have the n hat after. Well, I guess the n hat is included
No,
there.
no, the n hat's not included. So, in other words, to put this all together, ds vector is equal to ds without the vector times n hat. That's the notation, yeah.
Would that be applicable to like the mass of the surface?
Oh, sure. If f was, yeah, exactly. If f was the mass per unit surface area, then this integral would calculate the net mass of the surface. Yep. So that's the kind of integration that we would need to do to, for example, like calculate the moment of inertia for a for like a spherical shell. Right? We calculated the moment of inertia for a solid sphere in here earlier this semester. If we wanted to calculate the moment of inertia for a spherical shell, it would be that kind of integral we'd have to do. Okay? And we'll probably do that one of these days. Let me show you some examples then, now that we've got this all set up. So, number one, how about a plane? Right? So what's the plane? We could say x of uv is something like the point P, right? Plus u times a plus v times b, right? So this would be a plane which has the point P, and it has tangent vectors a and b. Oh. So, goodness gracious. To set up the surface integral on a plane, I mean, so we'll just, for the sake of specificity, yes. Benjamin, I'm trying to teach right now, buddy. So, we have, let's just, for the sake of specificity, suppose that we're going 0 less than or equal to uv less than or equal to 1, right? So that would do what? That wouldn't give me the whole plane. That would just give me like a little parallelogram, right? We would just be calculating if we limit the parameter domain like that, that would just give us this little parallelogram, right? And so to calculate the flux of a vector field through that, let's see here. What's the normal to the plane is my question, really. So we've got partial x, partial u, cross partial x, partial v. So what I'm going to be doing here in the next few examples is not like completely calculating, for the most part, completely calculating a surface integral. I just want to show you how to set up the normals for like some common examples, right? And then we'll be able to refer to these as we go on. So this one, what is partial x, partial u is what? Well, it's if, you know, p and a and b are constants, this is just a. And partial x, partial v is b. And that's it. That's the normal, right? So like in this situation,
No, you're not taking stuff.
I thought you were going to show the students how to behave, not how to misbehave. I'm confused. Let's see here. All right. So if you're following along in my notes, there's like page 356 to 357. What I'm doing there is I'm showing that this definition that I've given of the surface integral, it doesn't actually depend on your choice of parameterization, right? Because, you know, how many different parameterizations are there for a given surface? Yes, right. There's infinitely many. So it begs the question, how do I know that this integral doesn't depend on my choice of parameterization? Well, I proved that on the page 356 to 357. We'll look at that some other day. It's kind of technical. Let's see here. So, all right, so number one, which was not my number one in the notes, my bad. That's actually my number, well, number 4. This is actually number 4 in the notes. The one I do first in the notes is a common example, which is actually non-trivial in terms of how to calculate the surface integral. And that's the sphere of radius r.
How do you spell Dad?
How do you spell dad? Well, I think it goes D, A, yeah, D-A-D. You know spelling.
I was wondering about correct.
Yeah, you were correct. Let's see here. All right, guys. Goodness gracious. So number 1, in terms of examples, is the sphere. And by the way, this is number 2, actually. Well, I guess I'm going to follow the numbering in the notes just to not be weird. So I guess if I'm doing that, I have to admit this is actually number 4. My bad. That's all right. Oh no! I broke Taryn's brain. I'm sorry. I wasn't trying to do that. These are the issues. You know, this is the OCD notes issues. I'm sorry, but the color coding in the front row is just phenomenal this semester. Like, I have mad respect for the color coding. It's very nice. But anyway, so listen, what I was going to point out with number 4 is that the choice of which is u and which is v matters. Do you see that? If we switch the meaning of u and v, if I say v comes first and u comes second, then that makes the partial derivative switch. And it gets us b cross a instead of a cross b, which is minus what we said. Benjamin, you gotta stop, buddy. So what I'm trying to get at here, guys, is that the orientation matters. Like which side is up for the surface will change it for us. So traditionally, the sphere of radius r, Benjamin, you gotta go sit back down, buddy. The sphere of radius r, it has, we take the normal vector field, by default, the normal vector field is taken to point outward. All right, pointing outward is, by definition, the quote-unquote positive orientation for a closed surface. What's a closed surface? It's a surface which doesn't have an edge, right? Just like a closed curve doesn't have, in some sense, an endpoint, right? It closes back on itself. Same for a surface. Now, the question is, how do you parameterize a sphere? The answer is to do this. I'll use phi and theta. And so, I mean, I could use u and v here, but I'm going to use phi and theta because it's more, honest. And so we've got cosine phi. Oh, my bad. Cos theta, sine phi, r sine theta, sine phi, and r cosine phi, right? That is a good parameterization of the sphere. All right? And if we calculate the partial velocities here, Benjamin, you got to stop, my man. We've got r cos theta cos phi, r sine theta sine phi minus r sine phi Why? So that's the tangent vector in the direction of phi. The tangent vector in the direction of theta, increasing while holding phi fixed, is this. We have minus r sine theta sine phi, r cosine theta sine phi. Benjamin, stop, dude. 0. And then to calculate the normal to the sphere with respect to this parameterization, what do we get? We have to take partial x partial phi cross partial x partial theta. What's that? Did I do something wrong?
Is sine phi in the partial x partial phi supposed to be negative?
Oh, yeah, it's just supposed to be cosine phi, right? Sorry, I think something was distracting me. I don't know what it was. Yes, like you. So, the determinant, we got our x hat, we got our y hat, we got our z hat. And so I only want to work this out once, right? But I typically put this on the test. I mean, it's not unusual for me to put this on the test, work this out. Because you should be able to work this out. You need to make sure you can work this out. This is probably one of the, most central calculations of this part of the course. We come up against this example tons. And so I'd like to make sure we're all on the same page on how it's derived. But also, on the other hand, if I don't ask you to derive this, you're allowed to use it going forward, okay? So I'm saying two really different things at the same time. On the one hand, I'm saying after we do this, we can use it. But I'm also saying at the same time, after we do this, I want you also to be able to do this calculation I'm doing right now. I sure hope this works out pretty. So x hat, what we get is r squared cosine theta sine squared phi. And then the y hat minus, so let's see here, I've got a minus, how many minuses do I got? 1 minus for the determinant, 2 minuses for here, and a 4th minus because it's this one. So altogether plus r squared Sine theta, sine squared phi. All right. And then the z hat, I've got, you see how this goes? I've got a cosine times cosine, which gives me cosine squared, right? And I've got a sine times a sine, which gives me a sine squared. So when I take the determinant of this 2 by 2 subdeterminant, I end up with cosine squared plus sine squared. And what's left over is a cos phi sine phi. So I get r squared cos phi sine phi.
Daddy,
Yes,
I
Benjamin.
want to give out the tickets.
You want to what?
Give out the tickets.
Well, go give out your tickets then. Although I think you kind of lost all your authority as a police officer because
He's on his phone. I'm using the camera.
Yep. So, see well, anyway, this is why we should be really careful who we make police officers. Let's see here. R squared sine phi, it's, man, a bad police officer can be a source of so much trouble. My goodness. R squared sine phi, we can pull that out. What do we have left over? We've got a cosine theta sine phi, sine theta sine phi. Benjamin, go sit down, please. And then cosine phi here. All right. Can anybody recognize what that is?
That's the original parameterization.
That's the original parameterization without an r. But what it is though, right, is that at the specific point, if we're at that specific point, it's the vector which points radially outward, right? This is what I've called in our previous work rho hat. It's the unit vector in the increasing spherical radial direction. And so altogether, we have found the following. We have found that for the sphere, my bad. So right here is this is a formula for it, right? If you like, that's a formula for n, right? There's a formula for the unit normal to the sphere. But we can actually write that formula for the unit normal more elegantly in the following way. The unit normal is exactly equal to r squared sine phi, come on, r squared sine phi times rho hat. So that tells me, among other things, that Benjamin, you got to stop. The magnitude of the normal, right, is equal to r squared sine phi, right? And let's see here. Let me continue over here. I'd like to actually do an example today.
Daddy,
What?
I'm hungry.
You're hungry? Oh, well, the good thing is Mom's going to pick you up soon. Oh, hey, wait a minute. Miss Guthrie had a cookie. You can get her. You go get the cookie. Let's see here.
Go there?
If you want to.
I don't know.
Well, you better sit back in the chair then.
Oh, I actually remember.
You actually remember? Okay, we can go.
Hey.
Just making sure he gets there. All right.
It's like the wind.
Ay, ay, ay. So, ds in this situation is r squared sine phi d phi d theta. So this is the scalar surface area. The scalar surface area element of the sphere is that. So, for instance, application. Let's calculate the surface area of the sphere. How would we do it? So that would be surface area of the sphere would be the integral of the, add up the little ds's over the sphere of radius r. Oh, he's back. And so that is integral of r squared sine phi d phi d theta. What should I let my parameters range over if we want the whole sphere? You guys know, the spherical angles, how do they go?
0 to 2 pi, 0 to pi.
Okay, which one for this one?
Theta would be 0.
Oh, theta is 0 to 2 pi, okay. And phi is 0 to pi. So r squared is a constant, pull that out. We've got integral from 0 to 2 pi of d theta, integral from 0 to pi of sine phi d phi. So you do those integrals, and you've got r squared times 2 pi times 2. In other words, the surface area of a sphere is 4 pi r squared. Which is nice, right? That's actually kind of funny, isn't it? What did we figure out the volume of the solid sphere was? What was it? Four-thirds pi r cubed. Kind of like the area of disk is what? Pi r squared, right? You can compare that with the circumference. What's the circumference? 2 pi r. Do you see what's going on here? Yes, Benjamin. You're thirsty? No. Well, there's no water that I can let you go get. Sorry, buddy.
Should the volume be pi r cubed? Volume be pi r cubed.
Yes, 4/3 pi r cubed. No wonder people are having trouble seeing it. What? You know where they are? You mean in the break room? Okay. Go on.
Are you multiplying by r over 10?
No, we're differentiating. See, if you take the derivative with respect to r, you get 3 times 4/3, which is 4, pi r squared. Just like down here, if you differentiate pi r squared, you get 2 pi r. This continues to be true for higher dimensional spheres, like the hypervolume. The derivative of it gives you the surface volume of like higher spheres as well.
You can think of differentially expanding it.
Yeah, this doesn't work for other things. Like if you try it for a cube, right? Like a cube has the volume of a cube of side length x is what? X cubed. What's the surface area of a cube? Well, the surface area of a cube would be x squared plus x squared plus x squared plus x squared plus x squared plus, there's 6 sides, right? So 6x squared is the surface area of a cube, and yet the derivative of x cubed is 3x squared, right? So this relation between volume and surface area only really works for the sphere and the circle, yeah.
If you remember this
Help.
volume,
Help.
spherical coordinates, would it be?
Help.
What?
Can you open it?
Don't drink all of it. Save me some. All right. All right. So. All right. So moving on here. So that was. I suppose this is example 1.
I can't put my cookie.
In your belly, of course. Example 2. How about this? What if we. Example 2. Example 2. What if we have f of x, y, z equal to the vector field, let's say x, y, z. Okay, that's a pretty simple one. Now, one way we could do this integral is just explicitly from the definition, all right? So, and I want to do this, I haven't said yet, but, you know, find flux through you know, SR, the sphere of radius R, all right? So if we use the setup that I just have, we're supposed to do what? The flux of F, integral from 0 to 2 pi, integral from 0 to pi. We take our F, we evaluate it at the, we got R cos theta, sine phi, R sine theta, sine phi, R cos phi, right? I take the dot product with cos theta, sine phi, sine theta, sine phi, sine phi, and sorry, I ran out of room, poor planning on my part. And what goes here is R squared sine phi d phi d theta. All right, and we could take the dot product and we could do the integration, right? But let me show you a smarter way to do this calculation. We could also look at this instead, because I don't think I have quite enough time to do that one. We could also look at this integral from 0 to 2 pi, integral from 0 to pi, and we could look at it, we could use the spherical coordinate frame to make the calculation go nicer, all right? See, because what is this vector field in terms of spherical coordinates? What is it? It is nothing more than rho hat. That is rho hat. Because rho is the square root of x squared plus y squared plus z squared. Rho hat is xyz divided by the square root of x squared plus y squared plus z squared. That is exactly rho hat. And so what I'm up against here is, and if I take this and I evaluate it on the sphere, right? That's r rho hat. Because rho is equal to r is the sphere. So I can do r rho hat here, and I take dot product with, as we were discussing, this business, you know, over here, it is in fact
Daddy,
all of that.
Daddy.
Yes, Benjamin.
Rho
Rho hat.
I can see the thingy on your right.
You see what I wrote earlier?
Like
Oh, that's interesting.
I look this way.
So we can appreciate that what we're doing is what we have is a rho hat dot rho hat, all right? And what's rho hat dot rho hat? Well, it's 1. And so really the whole integral here drops back down to r cubed, integral from 0 to 2 pi of d theta, integral from 0 to pi of sine phi d phi, which of course is 4 pi r cubed. Now, if we took the, yes, Benjamin, if we calculated the dot product here, what should happen is we get this like collapsing through sine squared plus cosine squared of 1 down, so we just get to this integral. That's what would happen if we did it. Maybe we can see it if we just look at it. Right, this times that gives you a cosine squared sine squared phi. This times that gives you a sine squared phi. So that'll give you a sine squared plus cosine squared. It leaves you with a sine squared phi. And then the last term gives you a cosine sine phi. Oh, it gives you a cosine phi sine squared phi.
What about the R's?
What about the
You only have one copy of that.
only have one copy? What's that?
Like if you do the dot product, it seems like you only have one copy of R.
Well, there's an r squared down here.
Oh, so it's like multiplied by.
Yeah, that's supposed to be multiplied, but I know that this answer that I found is right because of, and this is a future looking comment, but this is exactly 3 times 4/3 pi r cubed. That is not an accident. So I'll just leave that as a comment that you can understand in about a week from now. All right, not yet, maybe. Well, my apologies for today. See how tomorrow goes. Thanks, guys.